My screen. Well, before I even do that, let me take roll first. Okay, today is the 9th. Let's see who is here. Hersey is here. Urani is not here. Kilcrease is here. Lackey is here. Luna Smith is here. Macias is not here. McKinnon is here. Morris is here. Powers is here. Renfrew is not here. Salvador is not here. And Spivey is here. Okay, so we're going to continue our discussion of nuclear chemistry. And let me see if I remember correctly. Share my screen first. If I remember correctly, okay, right. We ended last class with some problems dealing with radio. Wait, did we do radiocarbon dating? I know we did this. I remember describing these graphs, and I also remember discussing Geiger counter. I know we covered this, but I don't remember if we discussed any problems. Okay, so I think we need to go back to the assignments. So let me go to the assignment files, assignments. Number 8. This, okay, so, okay, I remember telling you that you guys need to do all those questions. Well, before we get to number 21, any problems with the ones before? Any problems? It's all about balancing nuclear equations. And just to remind you, when you're balancing nuclear equations, you have to make sure that the mass numbers are conserved on both sides of the equation and the atomic numbers are conserved. That's basically what it comes down to, all right? So any questions about any of these? Questions 1 through 20? No? All right. So let's look at question number 21, which says a piece of wood from an ancient artifact has a carbon-14 activity of 11.7 disintegrations per minute per gram of carbon. Current carbon-14 activity in fresh samples is 15.3 disintegrations per minute per grams of carbon. It gives you the half-life of carbon, and this should be carbon-14, by the way. And it says calculate the age of the wood samples. So just to remind you, the equation that we last discussed were a couple of equations, which basically 2 ways of saying the same thing. In this case, since they're talking about measuring the activity of the different samples, we can say that one way of expressing it is A is equal to A0 times e to the minus lambda t, right? Or ln A over A0. Oh, somebody's saying something. Oh, I'm sorry. Ooh, yeah. Okay. Maybe I'm muted here. Can you guys out there in Zoom hear me? Because somebody's saying they think I'm muted, but it doesn't look like it from here. Just type a 1 if you can hear me. Okay, at least Miss Lucky and Miss Luna. So I don't know who, well, let me see. And Mr. Powers. Okay, so I'm assuming I can be heard. So I don't know who said, somebody just mentioned that they could not hear me, so I don't know why. So I'm just going to continue. Okay, so oh, Mr. Kilcrease was saying that he thinks I'm muted. I think Oh, okay. So he just replied saying he can hear me now. Okay, good. All right. So what was I saying? Oh, so I was saying that there are two ways of expressing the equation for the decay of pretty much any isotope, in this case carbon-14. One of them is this. The other one is ln A over A0 is equal to minus KT, right? So of course, when you're reading these questions, you have to identify what is what. So the 11.7 would be the A, which would be the activity at a certain amount of time, and the 15.3 would be the A0, right? K would be the decay constant. In fact, I made an error here. In the case of nuclear decay, we should use lambda. We use K when it comes to chemical reactions, but we use lambda when it comes to nuclear reactions, all right? And remember also that there's a relationship between the decay constant and half-life, where half-life is equal to ln2 over K. So these are the equations we'll be concerned with. In fact, what I would do is use this equation first, because this equation allows us to calculate time very easily, right? Because that's what the question is asking for. The question is asking for the age of the wood sample. So what I would do is rearrange this to get T is equal to minus 1 over lambda ln A ln A over A0. All right? And what I would do next, this should be lambda here, I would put in the numbers here. As I said before, A is the 11.7, A0 is 15.3, but first I would find out what lambda is. So based on this equation, lambda would be equal to ln2 over the half-life, right? So wherever you have lambda, I'm going to put all of this right here, right? So the result would be minus 1 over ln2 over half-life, ln A over A0, and then I'll put in the numbers, minus 1 over ln2 divided by the half-life, which is 5730 years. And then I'll multiply that by ln A, which would be equal to 11.7 disintegrations per minute. So minutes to the minus 1, grams to the minus 1, divided by 15.3 minutes to the minus 1, grams to the minus 1. And then we do our number crunching. So I'm going to work out what's within the parentheses first, which is 11.7 divided by 15.3, and that gives 0.7675, and then I find the natural log of that. So this gives minus 1 over ln2 divided by 5730 times ln, times, because I did that already, times minus, how many sig figs should I want to start? Minus, it's 1, there's 3 sig figs, so it should be 3 decimal places. So minus 0.268. All right, and then I'll do the rest. So it is going to be 0.268 minus divided by ln2 divided by 5730. And according to my calculation, then of course the minus sign will change that to positive. So according to my calculations, and please correct me if I'm wrong, but the answer I got is, when rounded off to 3 sig figs, 2220, and the units would be years, because this is years here, all right? So this would be the final answer, 2,220 years, all right? So that's basically how that problem involving finding the age of an artifact based on carbon-14 dating is done. Any questions about this question? Any questions? Any questions? Any questions out there in Zoom? If not, I'm going to go ahead and clear this and scroll down. Let's see what. Okay, so this question says the half-life of a nucleus of radon-222 is 3.8 days. So that is the half-life. So this is T half. So the question is how many milligrams of a 5,000 milligram sample of radon-222 remains after 60 days. All right, so what I'm going to do is put a decimal point here to make that 4 sig figs. All right, so please make a note of that. Put a decimal point here to make this 4 sig figs. Okay, so it's the same equation or a similar form of the equation, but you'll notice that they did not give the activity as in the previous question. They gave you the mass, right? The mass is proportional to the activity, right? The greater the mass, the greater the activity. It's a literal linear relationship. So where we have something like A is equal to A0 e to the minus lambda t, we can rewrite that as M is equal to M0 e to the minus lambda t. We can replace the activities with the masses, right? Now in this particular case, the question is asking for M, right, at 60 days, right? So we can use this equation directly. So M would be equal to the initial mass, which is 5,000 milligram, times e to the minus lambda, we don't know what lambda is, times t. So let me go over here. Remember, t half is equal to ln2 over lambda. So lambda is equal to ln2 over t half, right? So let me work this out here. So ln2 over 60 days, right? That will be equal to 2 natural log divided by 60. So according to my calculation, this works out to be 0.01. I'm going to make that 2 sig figs, assuming that this is 2 sig figs right here, all right? So that will be 0.012 base to the minus 1, all right? So that would go here where lambda should be. So that would be minus 0.012 base to the minus 1 multiplied by, no, wait a minute, I made a mistake. This should not be 60. I'm sorry about that. This should be the half-life. 60 days is the time. The half-life is 3.88 days. So this should be 3.88 days. So let me redo this here. 2 natural log, 2 natural log divided by 3.88, and that's definitely 3 sig figs, so 0.179 days to the minus 1 would be the lambda. So I need to change this as well to 0.179 days to the minus 1, and then multiply by the 60 days. All right, so this is where the 60 days come in. So let's see what this gives. So 0.179 times 60 gives that, and then I find e to the minus that. And this part here, I just calculated, is equal to, let me do this again just to be sure, 0.179 times 60, and then I put a minus sign inverse. Okay, so this part I got equal to 2.1, that's 3 sig figs, so this should be 3 decimal places, 2.166. That's what this equal to, multiplied by 5,000. So let's see what that gives. Oh, it should be times 10 to the minus 5, by the way. Right? So 5,000 milligrams times 2.166 times 10 to the minus 5. And according to my calculation, the answer becomes 0.1083 milligrams. Let me do that again just to be sure. 5,000 times 2.166 times 10 to the minus 5. And that's what I've done. All right? So that's basically how that is done. Okay, any questions about this one? Any questions? Any questions? All right, let me see. It's okay for me to clear it. Oh, you take a picture. Okay. All right, so let me clear this. I'm gonna scroll down. Okay, so tell you what, based on what we have done so far, I'm gonna leave you to do question 23. Let me see here, 23. Okay, right, so do question 23, and if you have any issues, let me know. Now, I want to do one of these here, where you're asked to find the mass defect for a particular isotope and the binding energy, right? So let me just remind you what these different terms mean. The mass defect is basically represented by delta M, is basically the total mass of the nucleons in the nucleus minus the mass of the nucleus. All right? So that's the mass defect. And then the, what's the other term? Binding energy is equal to the mass defect times C squared, right? Now, there's another way of calculating the binding energy in terms of, and I don't see that here, but I know I showed you in the PowerPoint. Okay, let me not get into that. They did, however, show you this. I've never spoken about this before, but there's a unit called the mega electron volt. That's another unit of energy, right? And this is the relationship between the AMU and the mega electron volt, okay? Now, we can calculate the energy in terms of joules, but I think in the questions being asked here, let me just scroll down a bit. I think the questions are asking for you to calculate the binding energy. Well, they didn't specify the unit, so you could calculate it in joules, or you could do the mega electron volt if you so choose, all right? So let me scroll back up here. Okay, so let's do question number 24. It says tritium is an isotope of hydrogen. And just so that you know what tritium is, the tritium nucleus is this right here, 3,1H, right? So basically the atomic number is 1, but the mass number is 3, okay? So the question is asking for the mass defect of this isotope. So basically, if this were to be broken up into the fundamental particles, you're going to have 3 protons plus 1 neutron. I'm sorry, 2 protons. My mistake, what did I say? You're going to have 2 neutrons. So 10N and 1 proton, right? So that's basically the composition of the nucleus of tritium, right? So basically, delta M, what is delta M? Delta M would be the total mass of the products, right? The nucleons. And these are the values for protons and neutrons in terms of AMU. So I'm going to put 2 times for the neutrons, 1.008665 AMU plus 1 proton, for which the mass is 1.007825 AMU. And then I'm going to total that and subtract from that the mass of the tritium nucleus, which is given right here, which is 3.0160490 AMU. All right? So let's see what that gives. I'm going to add what's within the parentheses first. 1.0086665 times 2 minus, not minus, plus 1.007825 Okay, so this part here works out to be equal to 3.025155 AMU. And then I'm going to subtract from that 3.0160490 AMU. So let's see what that gives. Minus 3.0160490. And when I did that calculation, I got 9.106 times 10 to the minus 3 AMU. All right. So that answers the A part. All right. And what I'm going to do is rewrite that number here because I'm going to need it for the second part. 9.106 times 10 to the minus 3 AMU. All right. That's delta M. Okay. Any questions about this one? Any questions? Any questions? Okay. What I'm going to do is erase almost everything except what I have up here. Let me do that now. Okay, so let me scroll down. Okay, so the next question is asking, what is the binding energy of this isotope, right? So they didn't specify the units, so there are several approaches you can take. So the approach I'm going to take is I'm going to use the equation I showed you earlier, which is delta E, which is the binding energy, is equal to delta M times C squared. Now, the thing about this equation is that in the case of delta M, which we already have from the A part, that is 9.106 times 10 to the minus 3 AMU, right? What we have to do is convert this to kilograms. And I don't remember what the conversion factor is. I have to look it up. But basically, you're going to have the kilogram value up here, and that will be equal to 1 AMU. So let me go to tables in Canvas. And see if I can find tables. Fundamental constants, that's where it is. Okay, so, okay, here it is, the first one. Let me write that down so I don't forget. 1 AMU is equal to 1.66 times 10 to the minus 27 kilograms, all right? So that's the AMU equivalent to kilograms. So let me go back to this question. All right, so, okay. So up here, I'm gonna put 1.66 times 10 to the minus 27, which will be equal to 1 AMU. And then I multiply by the speed of light, which is always 3.00 times 10 to the 8 meters per second, and all of that squared. And then we do the number crunching. So 3 times 10 to the 8 squared multiplied by 1.66 times 10 to the minus 27 times 9.106 times 10 to the minus 3. And according to my calculations, the answer here is rounded off to 3 sig figs. So that will be 1.36 times 10 to the minus 12. And the units here will be joules because, just to remind you, kilograms times meter squared over second squared is the same thing as a joule unit. All right, let me just redo this again just to make sure that I'm doing this correctly. Times 1.66 times 10 to the minus 27 times 9.106 times 10 to the minus 3. And that's what I got, 1.36 times 10 to the minus 12, all right? Okay, any questions about this one? Any questions? Okay. The C part is asking for the binding energy per nucleon. Now remember, a nucleon is any particle that resides in the nucleus, right? So in this particular case, we have 3 protons, we have 2 protons and 1 neutron. So basically, we have 3 nucleons. So therefore, the binding energy per nucleon, delta E over nucleon, would be equal to what we just calculated here, which is 1.36 times 10 to the minus 12 joules over 3 nucleons. And that's it. So 1.36 times 10 to the minus 12 divided by 3. So according to my calculation, this works out to be equal to 4.53 times 10 to the minus 13 joules per nucleon. And that's how you do that. All right? Any questions? Yes, sir.
So the 3 nucleons are from the 2 neutrons and the 1 proton?
Exactly. All the particles that resides in the nucleus. Okay. Any other questions? Any questions out there in Zoom? Okay. So, I take it it's okay for me to clear this, right? All right, so let me clear this. Now, and basically what I just did for question number 24, same process for question number 25. Let me see here, question number 26, and that's it, right? So that's basically it for this assignment. So for those questions, it's the same process. The numbers are different, but the process will be the same because you're dealing with different nuclei. All right, there are a couple of things I need to cover in the remaining pages of this particular chapter. How do we make nuclei for different purposes, radioactive nuclei for different purposes, right? We're going to talk about different purposes or applications of nuclear particles, radioactive particles. But the way they're made is using a process called nuclear transmutation. So how do we make these different types of radioactive particles? We use this particular type of instrument known as a cyclotron particle accelerator. And they come in different sizes, depending on what you're trying to make. You can have one that is relatively small. When I say small, the radius of that would be about 3 to 2 meters, and then you have some which are relatively large in the order of miles, right? So it all depends on what you're trying to do. Now, let me just try to explain how this works. So here you have what are called 2 Ds, right? And the reason why they're called Ds is because they're shaped like the letter D in each case. Now, what they actually are, they are magnetic poles which can be alternating, right? So in other words, at one instant, one pole would be positive and the other pole would be negative, all right? And it switches, right? So it just goes back and forth in terms of the polarity of these Ds, all right? Now, what you'll have at the very center is a particle, right? And that particle could be something like an alpha particle. I think it's usually an alpha particle, right? Which is positively charged, okay? So what is done is, in the first instance, one of the Ds will be positive, the other one will be negative. So what will happen at that instant is that the alpha particle being positive will be repelled from the positive and move to the negative, right? And then there's a switch in the polarity, which means that the alpha particle now finds itself in a positive region. It will be forced to go to the negative Ds, and then you switch it again and it goes back and forth. And what happens as a result of the movement of the particles is that it goes back and forth and forms wider circles. And as it does so, it is picking up more and more energy until when it's allowed to escape one of the Ds, it hits the target, which contains a radioactive nucleus, all right? And then there's a reaction which occurs, which converts that nucleus into basically whatever you want to make, right? And I think I have some examples of radioactive nuclei that are made this way. So for example, in the case of the first example right here, the alpha particle would be here, and the nitrogen-14 particle would be on the target. And when the alpha particle gains in energy, as I described earlier, and escapes the Ds, then it will hit the nitrogen-14 particle and form oxygen-17 along with a proton, right? And this is also another example of a similar type of reaction where phosphorus-30 is made from aluminum-27. So basically, in these instances, what you're doing is making something which is unstable from something which is stable, all right? Okay, let me see here. So that's basically how that works. Oh, here's another example where carbon-11 is very unstable, right? So basically, in this case, instead of an alpha particle, you're using a proton to basically hit the target with the 14 nitrogen, and that results in the formation of carbon-11 along with an alpha particle. Okay, so that's basically what nuclear transmutation is all about. And these are just some other examples of different isotopes, radioactive isotopes that are made. And this is something that is done in industry because, as I said before, there are some isotopes that has some applications, for example, in medicine, which I'm going to allude to later on in this chapter, all right? Now, another thing I want to talk about is what is known as nuclear fission. And this is basically the breaking up of a relatively large nucleus by hitting it with a small particle like a neutron. And as a result of the spontaneous reaction, you're going to end up with smaller fragments and also an evolution of energy, all right? So this is one example of such a nuclear fission. This was first done in 1934, where uranium-235 is basically targeted and hit with a neutron. And then what happens is that the resulting product, it would be two smaller fragments. One is strontium-90 and the other one is xenon-143. And you'll notice that there are three particles that are produced as well, right? So in addition to the fact that you have one neutron hitting this particle, you're going to end up with these two fragments and three neutrons being produced as well. And the thing about this reaction is that these three neutrons can go ahead and hit other uranium-235 nuclei to produce three more neutrons, which will themselves continue the chain of reaction. So we have a chain reaction being produced as a result, and energy in each case will be produced. And this is actually used, this nuclear reaction is actually used in power plants, nuclear power plants, all right? In fact, years ago when I just moved here, back in 2011, there was a nuclear power plant operated by Duke in Crystal River, right? And but they decommissioned it like a couple of years after I moved here, which I kind of regretted because I was hoping to take some students there to have a look at it, but it's no longer in operation. Okay, so this is the equation for the reaction, right? And as you can see, energy is produced, a large amount of energy, which is the reason why nuclear energy is seen as a viable alternative to fossil fuels, all right? But we're going to talk about some disadvantages associated with this type of reaction when it comes to supplying energy. Of course, we can calculate the energy using the same equation as we did in the last example that we used, right? We find the mass defect, which would be the sum of the masses of the product minus the sum of the masses of the reactants, and then plug that into the delta M, which is all of this here. Delta M would be all of this times C squared, and that will give you the energy. And it turns out that the amount of energy that is produced in this reaction is 3.3 times 10 to the minus 11 per uranium nucleus. Now that might be small, but that's for each nucleus, right? So if you extend that to 1 mole, let's say, which would be equal to 235 grams, 235 grams multiplied by 3.3 times 10 to the minus 11, that would be equal to 7.7, let me do this again. I forgot to factor in what do you call it, Avogadro's number. So Avogadro's number would be equal to 1 mole, which would be equal to 235. So actually, you should multiply 3.3 times 10 to the minus 11 times Avogadro's number, which is 6.02 times 10 to the 23. And the answer I got here for each mole, so let me write it here, 2.0 times 10 to the 13 per mole of uranium, which is relatively large, all right? 1 mole would be equal to 235 grams. And as you can see, that's relatively large compared to if you were to compare fossil fuels and the amount of fossil fuel that you're going to need, it would be significantly less for the same number or for the same amount of energy, right? Oh, they did that there per mole. I didn't remember that they have that there. Okay, so, and here's a comparison. Let me just clear this here. If you were to use coal instead, if you're to use coal instead, 1 ton of coal will give you 5 times 10 to the 7 joules, right? So that's 1 ton compared to 235 grams. The amount of energy that you get for 1 ton of coal will be much less, all right? So that's the advantage of nuclear energy. The amount of material required is relatively small. Okay, so let me clear this, or more clear. Oh, I know what happened. Okay, so I described briefly the nuclear chain reaction that would occur in the type of reaction that I just showed you, right? So basically, as I said before, 1 neutron will hit the uranium-235, that will produce 3 neutrons. Each neutron can hit another uranium-235 nucleus, and as you can imagine, it just exponentially increases in terms of the possibilities of different reactions occurring at each step, right? So this is what we call a nuclear chain reaction. Each time you have an impact between the neutron and the uranium-235, it produces the amount of energy that I just described, and it just continues. So basically, collectively, in aggregate, you're going to get a large amount of energy being produced. Now, in order for you to sustain that chain reaction, you need to have a minimum amount of the nuclear material, the uranium-235, all right? If it is too small, then what will happen is that the chain reaction will not be sustained because the neutrons will escape the material before impacting other uranium-235 nuclei. So therefore, you need what is called a critical mass in terms of the uranium-235, which is a minimum mass which would be allowed for the sustaining of the nuclear reactions being occurring or continuing so as to produce energy, right? If the critical mass or if the mass of the uranium-235 is less than the critical mass, then eventually the reaction is going to stop and therefore not be sustained, all right? And this is just basically a diagram showing you how the nuclear reaction produces energy. So basically, the reaction that we just described will be taking place right here. This is where the uranium fuel rods are present and they'll be impacted by the neutrons, which will produce energy. That energy is used to basically heat the water that is surrounding it, and that water will lead into this container, which contains more water, and in this case, the water will be converted to steam, and that steam will be led out into a steam turbine, which generates the electric current, which will be fed into the external grid, all right? And you might be wondering, what is the role of the control rods? These are rods made up of graphite, a form of carbon. And basically, you use that to basically control the flow of the neutrons that are hitting the uranium-235, right? So you can either dip them or push them further down in order to slow down the reaction rate, or you can increase it, or you can push it up to allow the reaction rate between the uranium and the neutrons increase. So you can control the flow. You don't want it to overheat everything and cause an explosion as a result. So that's the role of the control rods made up of graphite, all right? Now here's a side-by-side comparison between the amount of waste that is produced, which is a very important concern when it comes to the use of nuclear fission, such as the one I just described. If you were to use a power plant to generate electricity, this is basically the numbers in terms of the waste that is generated, right? You have this much sulfur dioxide and this much carbon dioxide, which would be, let out into the atmosphere. And of course, that is a concern. And in addition, you have some ash, solid products, waste that is produced as well, which you'd have to get rid of, all right? In the case of a nuclear power plant, which generates the same amount of energy, the amount of waste in terms of volume is shown right here, right? So here you can see that one definite advantage of using nuclear power as opposed to, coal-fired power is the relatively small amount of waste, all right? So that's one advantage, but of course there's some drawbacks, right? And the biggest drawback when it comes to using nuclear power plants is that the wastes are radioactive. And not only that, but they typically have very long half-lives. So they'll be around for a long time, right? And when I say long half-lives, I'm talking about in the order of billions of years, all right? So, of course, if we were to embark on using nuclear power plants to generate electricity, then we have to be concerned with how do we deal with the waste, right? And back in the 80s, when Reagan was president, he proposed, I don't know if he proposed it, but it was proposed that there's a mountain in Nevada called Yucca Mountain, which was proposed to be a site for the disposal of nuclear waste, right? And basically what has happened over the years is that there'll be suggestions as to how to do it, and then there are people in Nevada, especially those people who live in Las Vegas. If I remember correctly, Las Vegas was like, or is about 100 plus miles from there. Those people are not comfortable with, the disposal of waste in the Yucca Mountain. Now, there's a video I want to show you, which goes into this in more detail. What time is it, by the way? Okay, should be enough time. I was looking online to see if I can find sources about what has been the latest in terms of decisions being made to hold on 1 minute. To how to dispose of these wastes. So I found one this morning and I posted it under the module section. Okay, here it is.
This video is brought to you.
You guys out there in Zoom, can you hear? Can you hear the video? All right, hold on 1 minute, let me play it again.
By Squarespace, whether it's a New Year's resolution or a lifelong passion, start your journey to website glory with Squarespace. Check out their wonderful all-in-one platform through the link in the description below. More on them in a bit.
Okay, you guys, do you guys hear that? Oh, they're in Zoom?
Yes.
Okay, good, all right. Now, the only thing I don't like about this guy is that he talks kind of fast, so that might be an issue. But pretty much what he said was pretty informative.
In terms of controversial topics, you'd be hard-pressed to find more contested subjects than the disposal of nuclear waste. The spent nuclear fuel from all of those weapons stockpiled during the Cold War and waste generated from nuclear power stations needs to be stored somewhere, as it can't be safely disposed of. The periods of time that we're talking about here are simply staggering. The most dangerous and long-lasting waste could remain radioactive for up to 1 million years. Even low-level waste could take up to 10,000 years, which is no doubt a difficult selling point for any residents living nearby to a proposed nuclear waste dump. The United States is one of the 2 biggest producers of nuclear weapons. There's an awful lot of nuclear waste that needs long-term storing, and one proposed site lies roughly 130 kilometers northwest of the Las Vegas Valley at a place called Yucca Mountain. The proposed Yucca Mountain nuclear waste repository was designed as a series of tunnels that would be able to accommodate large amounts of high-level nuclear waste, but has faced withering attacks ever since the project was approved in 2002, with just about every conceivable group voicing their opposition. project, which has already seen extensive excavation work, has been in limbo since 2011 when federal funding ended, leaving nuclear waste steadily building up across the country. That doesn't sound like a good situation. Like, as much as we hate having to store nuclear waste, we kind of gotta do it, guys. Nuclear waste disposal is a thorny subject and one with plenty of myths and hearsay. It's not difficult to see why the fear of living anywhere near radiation is enough to make almost anybody explode at the merest hint of a nuclear waste repository. With stories of Chernobyl and Fukushima still fresh in the mind, it can be next to impossible to convince people that nuclear waste can be stored safely. But the storage of the waste is probably one of the safest parts of the entire operation. The greatest nuclear disasters have come not from storage or transportation, but rather natural disasters and human error. The question of whether we should even be using nuclear energy seems to have died down in recent decades as the destructive power of fossil fuels has become evident. If nuclear energy is here to stay, as it almost certainly is, the question shifts to the waste issue. Surprisingly, or perhaps not, human thinking regarding how to dispose of nuclear waste hasn't changed much over the years. The prevailing concept remains roughly the same. Dig a giant hole, throw it all in, and cover it up and forget about it. Now, we're being slightly facetious here, but really not overly so. Most low-level waste uses near-surface disposal, which, as it sounds, means the waste is stored below ground, but still relatively close to the surface, usually in the tens of meters. This has been done in the Czech Republic, Finland, France, Japan, Netherlands, Spain, Sweden, the UK, and the USA. However, storing high-level waste is quite a different matter. This needs to be stored much further down, and here is where the problems lie. While numerous countries have explored the possibility, and some have even selected sites, only Finland is nearing completion of its own deep geological disposal site for high-level waste. And do not worry, we will certainly be elaborating on that later in today's video. It is estimated that 22,000 cubic meters of high-level waste is currently awaiting storage across 14 Western countries, while the amounts in China and Russia remains unknown, but is generally considered to be pretty substantial. What is clear is that we have absolutely no idea what we're going to do with all of this waste in the long run. As of early 2020, there were 57 nuclear plants in operation across the United States, totaling roughly 20% of the nation's total energy output. These reactors produce around 2,000 tons worth of waste every single year, and that's on top of whatever comes from nuclear weapons. There is a lot of waste in desperate need of a long-term home. Now, before we get on to Yucca Mountain, we should first talk about the Waste Isolation Pilot Plant, WIPP. Located 42 kilometers east of Carlsbad, New Mexico, the WIPP is the world's third deep geological repository after the radioactive waste Morsleben repository and the Schartast 2 salt mine, both in Germany, and is licensed to store transuranic radioactive waste from the research and production of United States nuclear weapons for 10,000 years. All three of these sites can accommodate low-level or medium waste, but not the most dangerous waste. The waste is kept here in rooms 660 meters underground and is thought to have cost in the region of $19 billion. Sometime between 2025 and 2035, when the plant reaches capacity, the caverns will be collapsed and sealed over with 13 layers of concrete and soil. And all that, as they say, will be that. While the WIPP is a start for vast amounts of American nuclear waste, it's nowhere near enough, which is why in the late 1970s, the Department of Energy began exploring Yucca Mountain. And if you want your websites that look clean, crisp, and not at all like a nuclear waste depository, it's time to head over to our friends at Squarespace. And that was quite the transition. Look, the new year is just days away. So whatever that new thing you're thinking about doing in that new year is, well, it's time to do it with Squarespace. Squarespace is the platform to use when you're ready to get started on your next web project.
Must apologize for this. You just slipped in an ad in between, in the middle of the this talk, so.
You're looking to get in and out quick without thinking too much about what your website should look like? Bam! Use one of their quick, beautiful templates to make a website that's fresh for you. Or maybe you're more of a hands-on person, you've got lots of opinions and ideas about how it should look. Well, Squarespace gives you all of the customization options you could ever want. Also, there's no updates, no patches, no tech BS to deal with. And once you're done setting up your website, tinkering with the design if you're so inclined, or if you're just playing with the colors, there are so many extra features that Squarespace provides so that your website can thrive. Email campaigns, patronage portals, social integrations, member-only areas, analytics, commercial options, 24/7 customer support. It's all there in one place, making it super easy to make an incredible website. And look, this isn't just another advertising partnership for me. When we launched the website for Mega Projects earlier this year, we did it on Squarespace, of course. And I've got no design skills, and I'm like, that looks pretty fly. If you want to check it out, just go to megaprojects.net and you can see what I managed to do with Squarespace. So when you're ready to launch and get started on our next project, go to squarespace.com for a free trial. And when you're ready to launch, go to squarespace.com/megaprojects and you'll save 10% of your first purchase of a website or a domain. And let's get back to Yucca Mountain. Yucca Mountain joined a short list of 10 sites across 6 different states that would potentially be able to accommodate 77,000 tons of nuclear waste by 2015. By 1985, that number had been whittled down to just 3, and President Reagan authorized extensive analysis of sites in Hampton, Washington, Jeff Smith County, Texas, and Yucca Mountain. 2 years later, Yucca Mountain was the last man standing. But even then, things were still a long way off. Initially, it had been hoped that Yucca Mountain could begin accepting nuclear waste in 1998, but that proved hopelessly optimistic. A long preliminary tunnel was dug within the mountain, and countless scientific surveys have been carried out to determine the feasibility of turning the depths of this mountain into the most radioactive spot on the planet. On the 23rd of July 2002, President George W. Bush officially gave the go-ahead for the project, but it hit a political brick wall almost immediately. During the 2006 midterm elections, Harry Reid, a Nevada senator and fierce opponent of the Yucca Mountain project, became Senate Majority Leader and didn't take long to voice his position on the proposed repository site, saying, "Yucca Mountain is dead. It'll never happen." As the United States and the rest of the world collapsed into recession, it seems the appetite for such a project began to dry up. After stating on the campaign trail that he would effectively cancel the project if elected, President Obama was informed upon taking office that things were not quite that simple. He couldn't simply cancel the project, but he could choose to not renew federal funding, which is exactly what he did in 2011. So really, almost nothing has happened regarding the Yucca Mountain repository in the last decade, except for the painfully high compensation the government has been paying to utility companies for not supplying a repository as promised. And the numbers here are quite extraordinary. The US government is currently paying these companies between $300 and $500 million per year to deal with their waste on their own accord. By 2025, it's expected that the total figure will have reached $24 billion. Now, it might be easy to grumble about greedy corporations here, but the truth is the US government stated legally that Yucca Mountain would begin accepting waste in 1998. 22 years on, not only is that still not happening, that promise is costing a staggering amount of money. The election of Donald Trump appeared to push the project back into favor, but his administration's efforts stalled in the US Senate. Trump then appeared to switch sides by stating that he agreed with the people of Nevada and didn't want the site as a dumping grounds. But in 2018, things seemed to swing 180, with his administration once again pushing for Yucca Mountain to be used. But yet again, efforts ran into a brick wall, and by 2019, the entire project just remains in political limbo. There isn't any nuclear waste in the complex, but what exactly does lie within Yucca Mountain? The main tunnel inside the complex is U-shaped, 8 kilometers long and 7.6 meters wide. The tunnel was dug using a tunnel boring machine measuring 120 meters in length and costing $13 million. Coming off the main tunnel are a series of alcoves where geological experiments took place. The emplacement drifts tunnels cut off the main tunnel where nuclear waste would have been stored were never actually constructed. This would have just been the start of the Yucca Mountain complex. The repository has a statutory limit of 77,000 tons of waste, but to reach this limit, it would need to have been roughly 64 kilometers worth of tunnels, so they're still quite short of that. Let's start on this one. Opposition for this project has been torrential from almost every corner. Consistent polls have shown that roughly 2/3 of those living in Nevada are against the repository, or should I say they're against the repository in their home state. Concerns have been raised about the environmental impacts, not necessarily now, but in thousands of years. The Department of Energy, DOE, has stated that for the first 10,000 years, the mean public dose of radiation would be 0.24 millirems a year, which would rise to 0.98 millirems year after year, both levels well within national safety guidelines. To give you some good comparisons, a hip X-ray results in a dose of around 83 millirems, while a CT head or chest scan is roughly 1,110. And in fact, there is natural radiation all around us. It's estimated that the average US citizen experiences background radiation of roughly 350 millirems without being anywhere near a nuclear facility. Then there was the question of scientific research. As early as 2005, doubts were raised about the falsification of some of the quality assurance documents of water infiltration. No significant significant proof was presented to back up these claims, and a series of white papers and further research certainly appeared to suggest that there had been no wrongdoing. In 2006, an independent group, Sandia National Laboratories, was brought in with the hope of calming the debate once and for all and delivering a clear and honest assessment. It did, but it didn't work. Public opinion has hardened considerably on the subject, and changing minds seems to be virtually impossible at this stage. Another contentious issue was how to transport all of this nuclear waste to Yucca Mountain. A rail route was considered the most viable, either through the Caliente Corridor or the Mena Corridor, which would have required the permission of the Department of Defense and the Walker River Paved Tribe, whose territory the line runs through. Road routes were also explored, but it was generally agreed rail would be better. If you thought the idea of storing nuclear waste in May Mountain was controversial, the idea of high-level waste trundling past homes on railway lines proved unpalatable for many as well. However, just by the way, an estimated 25,000 individual shipments of high-level waste have been made around the globe with zero incidents. But let's be honest, it's come down to politics and public opinion. Most people are vehemently against the project, and any politician who doesn't stand firmly against it is likely to see their dreams of a long political career cut rather short. So we know that Yucca Mountain might never be a waste repository, but what about what is happening in that other great nuclear superpower, Finland? The information that Finland is leading the way in terms of a waste repository might seem a little strange to some, but when you think about it, they do tend to have a habit of getting their act together up in Scandinavia. Finland currently has 4 nuclear power stations generating 27% of Finnish electricity, and like other countries around the world, they need to put their nuclear waste somewhere. And that somewhere is Onkalo Tunnel, a vast complex located 520 meters below the island of Olkiluoto, 230 kilometers northwest of Helsinki. Started in 2004, Onkalo Tunnel is now nearing completion and is expected to start receiving nuclear waste in 2023, where it will sit for an estimated period of 100,000 years. So, for the rest of the world, take note. That's how it's done. So let's get back to Nevada. Positions are now so firmly entrenched that it seems unlikely that Yucca Mountain is going to be used as a nuclear waste repository anytime soon. But while Nevada locals might celebrate that fact, it still doesn't solve the dilemma of what to do with more than 90,000 tons of nuclear waste currently held in temporary storage facilities across the United States. This is a major problem that needs addressing sooner rather than later. As the world tries to wrestle itself away from fossil fuel addiction, nuclear energy is likely to play an even greater role in the future, whether we agree with it or not. Unless we suddenly find a miracle use for nuclear waste, the United States is going to need to find a long-term repository quickly. But let's be perfectly honest, even if Yucca Mountain began taking waste tomorrow, its storage capacity is limited, and it's already less than the waste currently in the country. What is terrifying is that these decisions made now will have potentially life-changing and even global-changing effects in thousands of years. To give you an example of this, at the WIPP, which I mentioned earlier, they have designed special warning signs for future civilizations which might stumble across the waste dump. The signs include 7 different languages: English, Spanish, Russian, French, Chinese, Arabic, and Navajo, with space for further translation into future languages. They also include pictures in case these languages can't be understood, along with the screen, the painting of Edward Munch, a seemingly appropriate choice. If you think about how quickly civilizations rise and fall in terms of global history, that is, it's perfectly conceivable that the world may have changed to such a degree that this spot might not even be considered the United States anymore. Now, maybe we've destroyed the world and reverted to living in caves once again. It certainly makes you think about the actions we take and their future consequences. The squabbling over where to put this waste shows just how short-term humans can think. The fact that we have been using nuclear power for so many years and still can't come to a consensus on what to do with the waste speaks volumes about just how muddled this topic has become around the world, except in Finland. Nuclear waste is a headache that is not going to go away anytime soon. And as for Yucca Mountain, well, it looks like it's just going to stay a mountain. So I really hope you found that video interesting. If you did, please do hit that thumbs up button below. If you've got a suggestion for future mega projects, use the comments below. Also, please do check out our fantastic sponsor, Squarespace, who I'm linking to below. Thank you for watching.
So that's
5 words you pronounce wrong 2 years before your brain starts shutting down. Dementia is now becoming a new epidemic, according to the Mayo Clinic, where doctors have made a shocking discovery that...
all right. Let me get out of this here. Let me get back to my laptop. While this was going on, I was trying to find this, at least one news article on something that has happened recently. And what's going on? Okay. Oh, okay, here we are. How do I switch back to this here? Okay, so don't know if you have been following the news concerning what the current Trump administration has been doing with respect to government agencies and so on. And they've been going left, right, and center, you know, firing people and so on. And one of the institutions affected was this institution right here, which is the National Nuclear Security Administration. And their role, among other roles that they have, is to basically deal with the nuclear weapons stockpile, which includes, and I think in addition, they have to, they're responsible for monitoring waste and so on. So in my opinion, it's a big mistake that they made to fire wholesale people who are responsible for this very critical role that they play. And, you know, it just goes to show that sometimes people in charge don't understand what's in sense. Okay, what time is it? 9:03. So let's see here. Okay, one last thing I want to talk about, and then we'll call it a day. And this has to do with what is called nuclear fusion, which is the opposite, so to speak, of nuclear fission. And in nuclear fusion, basically what you're doing is combining two lighter nuclei to form a heavier one. And this is basically how we get our energy from the sun. The sun is basically a huge nuclear reactor, for lack of a better way of describing it. And these are the reactions that takes place, which has correspondingly a large evolution of heat energy. So for example, you can have two deuterium nuclei coming together to form the product shown, and this is the amount of energy released. And this, of course, is the energy per particles. So you'd have to multiply by Avogadro's number to get on a per mole basis. This is another reaction that takes place, which produces energy as well. And the last one is where lithium come together with deuterium to form two alpha particles, and this is the amount of energy that is produced as a result, all right? So that's basically what happens. And therefore, as a result, I think there's another one. Oh, no. As a result, scientists have been looking at using that idea instead of nuclear fission in order to produce energy, alternative sources of energy, right? And people have been working on this pretty much all over the world. One example is this particular device called a tokamak, which basically brings the nuclei together, that the same nuclei that I just showed you, which would cause the formation of energy in the sun, bring them together so that they're forced to react and therefore produce energy. The problem with this that they're facing is that in order for, well, firstly, the nuclei would have to be in the form of ions. That requires a large amount of energy to basically form the ions. And then you have to basically force those ions to come together because they're all positively charged and come together, react, and then form, produces energy, all right? So that requires energy cost at the front end. But at the back end, the hope is that energy would be produced. More energy would be produced than used up, basically, all right? So that is one instrumentation, and there are others. And in fact, they've been successful actually in about 2 years ago, and there's another video that I wanted to show you, but I guess you guys can watch it on your own. I'll just show you where that video is. There's a video which has two persons speaking. One of them is one of my favorite persons ever. Let me go to files, modules. Okay, nuclear fusion. Is that the one? Hold on 1 minute. Yes, this is it. So my favorite person is, I don't know if you know this guy, Neil deGrasse Tyson, right? He's an astronomer, but his claim to fame is the fact that he's very effective in terms of communicating scientific experiments and principles and so on to everyday people. That's a skill I respect because I don't have that skill, all right? And he talked about the latest developments in nuclear fusion of the type I just described. And we won't have time to watch it here. So what I'm going to do is give you the assignment of watching it so that you can learn about that development. I think what he was describing is a recent discovery about 2 years ago in Japan, if I'm not mistaken. And I've also included in the module section some articles concerning other nuclear fusion breakthroughs, right? So you may want to read those as well. Basically, they're describing different scientists in different parts of the world, basically chasing this goal of carrying out nuclear fusion so that it produces energy as an alternative source. One particular advantage of this particular process is that it does not produce the amount of waste that would be produced by nuclear fission. So that's why people are working feverishly at developing this particular technology so that it can be applicable in terms of producing energy for different, sources, different reasons, electrical energy, or even the possibility of cars or motor vehicles powered by nuclear fission. So those are just some examples of the type of research that's being done. All right, I'm going to stop here for today. And there's just a couple of things I need to finish up on this chapter, and then we'll move on to organic chemistry. All right, so that will be it for today. And we'll continue on Monday. Okay, and for you guys out there in Zoom, I'm going to sign off now.